Hi everyone, this is Karthik. Welcome back to the channel. This video is going to be about Google Kickstarter round G 2020 and I will be discussing all the four problems of the round. I'll be giving you a quick editorial to all four of them and I would try to explain in the best possible manner. Meanwhile, you can hit the like button, subscribe to the channel. Also in the comment section, I would like to know if you found the particular round easy, difficult, interesting or boring. It would be a nice discussion to have. I would share my analysis too if you guys ask me. I'll let you know in the comments. So let's get started with the problems already. So the first problem was kind of not very hard. You needed to find out all the number of substrings of the form kickstart. Okay, so the string must start with a kick and end with a start. In between, it doesn't matter what comes. So it was not that hard, but if you do the brute force, it would definitely time out. What I did was I found out all the indices where a kick occurs and I found out all the indices where a start occurs. I stored them in different vectors. So here is a part, store indices where kick occurs in the input string. So kick might be occurring at places like I1, I2, I3 and so on. Same way, find out all the indices where a start occurs. It might occur at J1, J2, so on. Now think about a kick. If I have for a particular kick that occurs on index I, if I have let's say 5 starts that begin after the index I, then all these starts can be used as a end of a substring where I can use the kick starting at the ith index and I could basically form 5 such substrings, right? So if you read this C point, for every kick that occurs at the ith position, if there is some start to the right of the ith position or to a position j greater than I, then all these starts can be used along with this ith kick to form a valid substring and I can add these to the answer. Now all I needed to do was count all such ij pairs and that was the answer. So how do we do that quickly? I'll show you in code that makes it much easier. I am not particularly proud of this code, but it is what it is. Yeah, so first of all, I found out all the indices where a kick occurs. I stored it in this vector. Then I found out all the indices where starts occurs and I stored it here. Now for every kick that occurs at the xth position, see how many, the number of starts that occur to the right of the xth position or at a position that is greater than x or to the right of x. So for that I used lower bound. I found out the first index in the start array which is greater than x, and then I found out the number of such indexes in my start array. I added that to the answer and I was done. So not very hard. Let's move to the second problem now. Second problem was probably one of the easiest problems according to me that came in Kickstart. So if some of you were not able to solve the first and therefore did not try the second, it's hard luck, but second was, according to me, second problem was much easier. Second problem said that you have a grid and you can, in the grid, each cell has a few number of coins and definitely positive number of coins or zero number of coins. Now you can pick any position to start at. From the cell ij, you can either move diagonally down or diagonally up. These are the only moves allowed and you can move as many times as you want. You can start at any position. All you want to find out is what is the maximum number of coins you can gain. And if you think about it for a while, all you need to do is find out the sum of coins at each diagonal, and whichever diagonal has the best answer, basically whichever diagonal has the most number of coins, that is your answer. And that was all. I'll just show the code also and we'll move to the next. So first I take the grid as the input, then for every diagonal I find out what is the sum of at that particular diagonal using this particular simple function, and we're done. Among these, whichever was the maximum, I displayed it. Let's move to the third question. This was the one I found interesting. In fact, it took me some while to solve it because I'm pretty much out of practice nowadays. You should never stop practicing when it comes to competitive DSA and algorithms, data structures and coding, you should never stop practicing, never. This is something I should never stop practicing, but I did, so it took me a while to solve it. But anyway, the solution overall is interesting. The implementation, I don't really care about it for now. So we have W wheels and each wheel has a value. These values are come from a natural number set and the values could be 1, 2, 3 so on till n. N is also given in the input. So each wheel has a value Vi. In the test set 1, W is up to 1000 and so is the number of values up to 1000. All you need to do is you need to move the wheels and try to bring all the wheels to the same value, and the cost of doing this should be minimum. You can bring them to any value, but the cost of doing this should be minimum. At the cost of 1, you can take any wheel and move it either right or left, basically increase its value or decrease its value, and these values wrap around. So if a wheel has the value n and you try to move it right, it reaches the value 1. That's the thing. And if a wheel has a value 1 and you move it backward, it reaches the value n. Now you need to find out the minimum cost of setting all these wheels to the same value. For test set 1, it was pretty simple because the number of values are very limited. There are only 1000 valid values at most, because n is up to 1000 and n shows what are the values a wheel can have. So what you can do is, first of all, see this. What is the minimum cost of setting a wheel to value x? You can read this out. Now I will try out all the valid x values. That means I will try out x equal to 1, x equal to 2, x equal to 3 and so on till x equal to n. For x equal to 1, I will try out what is the cost of setting all the wheels to value x equal to 1. Once I found that out, I'll store it, then I'll find out for x equal to 2, so on till x equal to n. Among these, whichever of the x value was the minimum, basically setting all the wheels to whichever x value was the minimum costly or the least costly, that is my answer. The solution here is w into n, big O of w into n, but that does not work for test set 2 because n is up to 10 power 9 now and big O of wn would not work. Now what? So the observation here is that, and yeah, if you want the proof for this, you can ask me in comments. For now, I want to omit the proof, but I can guarantee you that a proof does exist. But the observation here is that you don't actually need to try out all the values x equal to 1, 2, 3, so on till n. You just need to try out the values x equal to v1, v2, v3 and so on till vn. Here vi is the value of the ith wheel. Basically the wheels had an initial value. In the final configuration, or the value x that you choose will be one of these values on the wheels that initially was there. So if the first wheel had a value v1 and the second wheel had a value v2, so until the nth wheel, you just need to try out these w values, sorry vw. You just need to try out these w values, and test set 2 will now work in big O of w squared. Because there are w values, you need to try out all the w values for all the w wheels, and it takes w squares using the same solution we had in test set 1. Cool. Now moving to test set 3. W square would again not work, right? So what I did was, I can sort all the wheels according to the initial values on the wheels, right? So imagine that let's say you have sorted down the wheels and you can say, okay, the first wheel has a value v1, second has a v2 and so on till the last wheel has a value vw, and assume that v1 is less than equal to v2 less than equal to so on till vw. So I've basically sorted the wheels according to the initial value they had on them. Let's see how this will help us. So once it's sorted, the situation would look something like this. Imagine a road and the wheels are there. So the road starts at point 1 and ends at point n. You have these wheels from v1 till vw, where v1 less than equal to v2 less than equal to v3 so on till vw, and the road looks something like this. You need to move either the wheels to the right or forward or left backward and make them reach a single value, right? Make them all of them reach the same value, and these values, as we discussed in test set 2, will either be v1, v2, v3 or so until vw. It is going to be one of these values. But if we do it in the brute force manner, it's big of w square. That does not work. So how do we try each value x equal to vi? So this is the situation how it looks like. Okay, I am trying to set bring all the wheels to the value vi, so that ith wheel does not need to move. All the wheels to the right need to reach ith, and all the wheels to the left also need to reach the ith. Now think about these wheels here, from vi plus 1 till the wth wheel vw, right? Think about these wheels to the right of vi. They can either go backward and reach vi without wrapping around, or they can go forward, reach n, wrap around to 1 and then reach vi, right? They have two ways. Either they will go backward or forward. Now think about a wheel j that belongs to this particular region from vi plus 1 till vw. Okay, I'm thinking about this particular region here, and there is a wheel vj. Okay, assume that it is optimal for the jth wheel to go backward instead of going to n and then going to vi. Assume that for the jth wheel it is more optimal to go to vi, right? In that case, any wheel that is from vi plus 1 till vj minus 1, for all those wheels it is optimal to go backward only, because if it was optimal for them to go forward, then vj would also be going forward, since it's more optimal. Basically, if it's more optimal for vj to go backward, that means any wheel that is from vi plus 1 to vj minus 1, they will also be going backward, because if they went forward, it is definitely a higher cost for them. And that's the idea. So what you can do is, you can find out the first wheel in this region, and let's call that the jth wheel, that does not go towards vi, that goes towards the right hand side, and any wheel to the right of it will definitely go towards n and then wrap around and come to vi. We just need to find out the first wheel vj, for which it is more optimal to go to n and then reach vi instead of going backward. And how can we do that? We can do a binary search, of course, right? Since there comes a point till which all the wheels wanted to go back, but there comes a point at which a jth wheel wants to go front, we can use a binary search to find out the value of the jth wheel, or which is the first wheel who would like to go towards the right and then wrap around and come to vi. Basically the first wheel for which it is more optimal to do so. Cool, we will be able to find out vj, but still, how does that help me find the answer, isn't it? That's what you would be wondering. Okay, we can find out for these wheels it is more optimal to go backward, while for the others it is more optimal to go forward, but how does this help us get the answer? That is the point. So by binary searching I will find that out. Now how does this help? Think. Pause the video and think for a while. How does this help? Here is the answer. Binary search, find out the first wheel that wants to go towards the right. Now do one thing. Evaluate the costs for the wheels to reach 1. Okay, what I will do is, I will build two arrays, prefix and suffix, and prefix at I would represent what is the cost of taking all wheels, or the first I wheels, cost of taking first I wheels backward to reach position 1. Okay, this is what I'm going to name prefix of I. Similarly, I'm going to have a suffix of I, and that would be the cost of taking the wheels from ith till the wth wheel to the position n. So I define these two prefix and suffix arrays. Now think that all the wheels from I plus 1 to j minus 1 wanted to go backward. It was optimal for them to go backward, right? So what I can do is, I can find out the cost something like this. I can say that prefix of j minus 1 represents what is the cost of taking the first j minus 1 wheels back till the position 1. Since I'm not concerned about all the first j minus 1 wheels, I'm only concerned about the wheels in this region. So I subtract the cost of taking the first I wheels to position 1. This gives you the cost of taking the wheels in this region to position 1, right? But I don't want to take them to position 1. I want to take them till the position where Vi currently is, basically to the position Vi. So what I'll do is I'll count the number of wheels in this region, which is very easy to count, and the effort that they were taking before to reach till 1, I would remove that region, and I can definitely very easily get the cost of reaching till Vi. Basically, if there are a X number of wheels in this region, then the overall cost becomes this thing, cost of taking all these wheels till the position 1 minus X times taking these wheels till the position Vi and then taking all of them to the position 1. So it's basically Vi minus 1. You can remove this cost because you don't really need to take them to the first position, you just need to bring them to the position Vi. And this gives you the cost of moving the wheels in this region I plus 1 to j minus 1 to the position Vi, and this is a big O of 1 operation. Calculating the prefix and suffix is big O of n, but it is done only once in the startup. And the binary search is login, so you could basically find out the wheels that need to go backward, the wheels that need to go forward, and you could use these prefix and suffix arrays to find out your answer. And guys, that's all. Overall your solution is w times log something, maybe w log w, anyway whatever it is, but hopefully you get the idea and you can find out the answer. I can show you the code, but my code wasn't really neat this time. Yeah, so I calculated the prefix and suffix arrays in this pre-process step. Then this back cost is what is the cost if the wheel moves backwards, and yeah, now this is get forward lock 1. This was what is the first wheel that would go rightward instead of coming back to Vi. This finds that. And this get forward lock 2 is basically for the region from the wheels V1 till Vi minus 1. For now we were just talking about the right portion. This evaluates the first wheel in this region from V1 to Vi minus 1 that would like to go forward towards Vi and not backward and wrap around to come to Vi. The concept is the same, so I am not explaining it again. This evaluates the forward cost. What is the cost of going forward for all the wheels from positions I till the j, for the ith till the jth wheel to reach the position lock or Vi. Hopefully guys you understood. If there is any doubt in this one, let me know in the comments. Let's move to the next problem now. Merge cards. So test 1 was very simple. You just need to try out all the possibilities. I'll show the code for that also. Trying out all possibilities is, as they said, that merge any two cards at random and see what score they produce. Try out all the possible games. The number of games should then be basically among all the games, whatever you score, keep adding the scores, all the possible scores and the possible games, count the number of games that occur, and then overall divide them by the total number of games that occurred, the overall score. I'll just show you the code, it becomes very easy to understand. This is a brute force, yeah, brute solve. So you take in a vector v and current score is 0. If the vector is already 1, there is nothing left to merge, your game is over. You add 1 to the number of games played, you add the score to answer and return. Otherwise, you at random, or basically you try out every possibility. So you take the ith card and merge it with the I plus 1th card. So you are left with this new temp array where all the cards are same except that the ith and the I plus 1th card are merged in here. Add this merge possible to the score, add this to the score Vi and Vi plus 1, add this thing to the score and pass it forward. Keep evaluating the answer and the games. At the end, display answer divided by games and you're done. This was the brute force solution, but this works only for test set 1. Now let's talk about test set 2. So we are going to define dpij as the expected value of score if we add only the array ai to aj. So imagine that you don't have the entire array, you just have the array from ai till aj and define dpij as the answer for that particular array. Okay, what is the score, expected score you would get if you played the game out of this particular sub array. Now before we move ahead, the score for a sub array with only one element is 0 because there is nothing to merge. the score for a subarray with two elements, something like this, is basically the sum of the two elements, right? Because there is only one game possible, and that is to merge these two. So 3 plus 5 equal to 8. So this gives us some of the base cases, right? Now we know that the answer is going to be dp of 1 comma n, because the problem is asking us the expected value of score if we have the entire array from 1 to n, and by definition this is dp of 1 comma n. Now how can we actually evaluate this? So observe that the final move of the game is going to be two cards left, and one of the card is going to be the prefix from a1 till ai, and the remaining portion is going to be a suffix merged into one card, that is from ai plus 1 till an, right? So these two cards will be merged in the end. The final move of the game will always be this: a prefix and the remaining suffix of the array getting merged. Two cards, one card which was made from the prefix, another card which was made from the remaining suffix getting merged into one card, and the game getting over because we have only one card left. This is the final move always. If you think about the initial array, the final moves, there are, if the array size is n, there are n minus 1 final moves. So either the first card and the remaining n minus 1 cards get merged in the final move, or the first two cards and the remaining n minus 2 cards get merged, and something like that, or like so until the first n minus 1 cards and the last one card get merged in the final move. We know the final moves, right? You can read this one, although I've already explained it, so would not matter much. So more formally, the final move is this: merge ai to ak. For dp for the array ai to j, the final move is this: ai to j, the final move is going to be this, right? You merge a prefix of it and the remaining suffix into one. Now each of these moves are equally likely to happen. So what I can do is, if these are going to merge, the prefix and the suffix, I could find out what is the answer for this prefix, the answer for this suffix. I could find out these expectation values, right? Then on merging them, of course I would get a sums equal to the sum of the entire array or the subarray which I was focused on, plus the expected value of the left part and the right part, which is going to make my overall answer, right? So let's move forward and I'll explain this recurrence to you now. So for dpij, the answer for the a subarray ai till aj, you're going to have a sum ij definitely, because you're merging two parts and overall their sum becomes sum ij, the sum of the elements from the subarray ai till aj, right? This is definitely going to be there because your the merge step itself produces this thing. Plus there are there are these many possible ways, and you're going to merge this prefix or this suffix, right? Where k goes from I to j minus 1. This is going to be a recurrence, and I'll show this in a solution now. Yeah, this is the solution that passes test set 2. You're trying to find out the answer from for the subarray I to j. These are the base cases. If the subarray is of size 1, if the subarray is of size 2, if the answer is already calculated, and finally trying out all the possible final moves, right? And overall, among all these final moves, calculate the overall sum as the answer and divide by the number of possible moves. That gives you the expectation value. So that's it. This gives you the solve method. This runs in n cube time because of the summation. And I know guys, some of you might be having doubt in this recurrence due to lack of the expectation or probability theory. So you can ask me in the comments, but if you have doubt with this recurrence, I guess the first move should be try and understand expectation values, probabilities. I can make a video on that, but if I try to include each and every step here, then this gets too lengthy, right? So for now I do omit few of the things, but I'll be happy to help in the comments or probably come up with a video that could back up the knowledge. Now this was all. this could run in n cube, and we have this method that actually does the thing. How do we actually optimize it to n square? Let's see how we can do it. I can write this summation dpik to dpik plus dpk plus 1j in this format. It's summation dpik plus summation dpk plus 1j for finding dpij. Now what happens is that I could open this summation. This thing becomes, this summation dpik becomes dpii dpi plus 1 so on till dpij minus 1. Try opening it, and if you try out all the possible k's, this is the thing that comes out. Same way, if you try it out for all possible this summation, and you try out all the possible values of k goes from I till j minus 1, you get this particular value here. Now what you can do is you can write a bottom-up code, and in the bottom-up code you will first evaluate the answer for all the subarrays of sizes 1, subarray of sizes 2, subarray of sizes 3, and meanwhile you will keep evaluating these prefix values side by side, so that when you need this value you have it already calculated. And once you evaluate dpij, imagine that you already have this thing in some prefix array. So I already stored this thing in some prefix of I, right? Imagine that I've already stored it, and now I'm trying to find out dp of ij. Once I've found out dp of ij, I would update this prefix of I to also hold the value dpij. And next time when I'm trying to find out answers to all the subarrays of sizes plus 1, that means greater than the size of this subarray from I till j, that means I would be trying to find out dp of I comma j plus 1, and that time I would require sorry, I would require this thing, this plus dp of I comma j, right? And I would already have this stored in prefix of I, and next time I evaluate dp of I comma j plus 1, I would also store that in the prefix of I. Same way, I would have a suffix of j, and I would store these values in suffix of j, and we're done. This will help us evaluate the recurrence in big of 1 time. The transition time becomes big of 1. Overall it becomes n squared. So guys, hope you liked the video. Make sure that you like, share and subscribe. Definitely motivates me to make more content. I need to buy a tablet too, but if you guys don't subscribe, I cannot just invest right now. So do subscribe, do like the video, and let me know in the comments if you found it helpful, you want me to explain some of the concepts better, anything. Also the code, the fast solve, I try to evaluate the answers for subarrays of sizes sz. So I evaluate the answers for all the subarrays of sizes 1, 2, so on till n. I evaluate the answer for a subarray of size sz that begins at the ith position. Meanwhile, I'll keep building these prefixes and suffixes as described in the notepad. So hopefully you like the video, guys. Bye.